Hello and welcome to lesson 8.2, Equations of a Plane. So today what we're going to do is we're going to see what the equation of a plane is and how it works out and how we can draw it. So in 3 space, or in R cubed, a plane is like a sheet of paper in 3-dimensional space that can be defined in many ways. So the plane x equal to 4. Well, first of all, I'm going to label this grid. Okay, so there's our values. Okay, the plane x equal to 4 means your x values are always the value 4. And your y values can be anything, and your z values can be anything. So some points that are on there could be anywhere along this line here. These have the various different y values, but they have the same x values. But also they can have every kind of z value. So that means, let me draw this line first. You can extend it upwards into all the z values, or even downwards for that matter. We tend to usually use the upwards values to show it. And therefore you can just draw it as a sheet of paper, like so. Now technically it's still going in all directions, inwards and outwards, and upwards further, out towards the left and outwards to the right further, and even down further. But usually you just draw a sheet of paper like this. There are various different programs that you can use to draw these kinds of things. One of the ones that I suggest you use is called Geogebra 3D. Just look at how you can draw lines and vectors in that kind of program, and then you can draw some kind of graph like this. Some points that actually lie on this equation x equals 4 is a point like 4, 0, 0, or 4, 1, 0, or 4, 3, 2, or 4, 7, and negative 5. As long as the y and z values are different, they can even be the same. But 4 is always the x value. So this describes the equation of a plane. So let's take a look at a different one. Again, I'm going to label my axis before I continue. Okay, so now to draw the plane given by x plus 2y equals 4, I'm going to rewrite this as x equals 4 minus 2y to begin with. So that means whatever y value I choose, it'll also choose the x value I have for me. So if I choose y as 2, let's say, my x value would be 0. And I can choose any number I want for z because it doesn't matter in the equation. So I'm going to choose the point 0, 2, 0, which is this point right here. Now if I also chose my y value as 0, my x value in that case would have been 4. I'm also going to choose the intercept right there, 4, 0, 0. So these 2 points that I've drawn on here are part of this line, are part of this plane. So I'm going to start out by drawing that line. Because my z values can be anything I want, so I can have 0, 2, and 5, let's say, or 4, 0, and -3, this would go up and down from this line that we see here. Now, it's not of major importance that we actually know how to draw these items, but I'm just showing you how to draw them. The idea here I want to get out is how these planes look in terms of, or how they're related to other axes or other planes. So let's go back to the first one. The first one you can see is parallel to the y-axis, and it's also parallel to the z-axis. Because it's parallel to two axes, it's also parallel to the y-z plane. So this is how you can describe it. Whereas looking at the second option, you can only see that this one is parallel to the z-axis. Okay. So we notice that the scalar form of a plane is given by this expression, ax plus by plus cz plus d equals 0, where again a, b, c, and d are integers, and the values have to be in the lowest terms, and the leading coefficient must be positive. Okay, so moving right along. So what we're going to do is use this information to determine two vectors that are parallel to this plane. So in order for a vector to be parallel to the plane, it must actually lie in the plane. So first of all, I'm going to find some points. That just means we have to just choose values of x, y, and z that would make this expression true. So some possibilities are, I'm going to choose ones like 3, 0, and 0. That's one possible number. And you can choose any numbers that would work out to make this true. So another possible point that might work is 3, 2, and 1 would be another possible point on the plane. And let me pick something else that's just totally different. Let's change this first number to a 5. That'll give me 15 in the first number. That means I've got to subtract off 6 to make it 9. So let's make this a 3 and this one a 0. So these are some points on the plane. You can choose any points that fit on the plane, and there's an infinite number of options that you can choose. Now to get two vectors that are parallel, well, all you have to do is just subtract 2 points from each other. So let's take 3, 2, 1, and subtract the vector 3, 0, 0, and you get the vector 0, 2, 1. This is parallel to the plane. Also, if I take any two other points, 5, 3, 0 is a vector, minus 3, 2, 1 as a vector. Another vector that's parallel to this could be 2, 1, negative 1. And again, there could be an infinite number of different options that you can have here. Okay, so moving along. Now, just like in two-dimensional space and three-dimensional space, you can write vectors in other formats. You can do the same thing with planes. So in 3 space, if A and B are two vectors that are non-collinear, and P sub 0 is a point in 3 space on the plane, then the vector A and B can be expressed as a multiple of the original OP sub 0 plus some scalar multiple of A plus some scalar multiple of B. So another way of you can writing this is x, y, z is equal to some original point, x sub 0, y sub 0, plus z sub 0, plus some scalar multiple of the vector A. Let's call them A1, A2, and A3, plus some scalar multiple of the vector B. We'll call that B1, B2, and B3. Well, what you notice is this looks like the vector form of a line, except for one extra dimension. This is the vector form of a plane. And you can also create parametric forms. Of a plane, just by separating the x, y, and z components. So x would be equal to x sub 0 plus s times a1 plus t times b1. Y would equal to y sub 0 plus s times a subscript 2 plus t times b subscript 2. And z is equal to z sub 0 plus s times a3 plus t times b3. And therefore you can separate it into 3 different parametric equations. Therefore, looking at both the x, y, and z's separately. Okay, so we're going to find the vector equation of the plane that contains the line from the point 2, negative 3, 4 in the direction of 2, 0, negative 7, and also contains the point negative 1, 1, and 5. So, to come up with a vector equation. Vector equations require a point and 2 directions. So one of the directions is already given to you. It's 2, 0, negative 7. The other direction is not given to you, but it contains these points 2, negative 3, 4, and negative 1, 1, 5. So to figure out your other one, just take one point as a vector and subtract it from the other point, again, as listed as a vector. So 2 minus negative 1 is 3, negative 3 minus 1 is negative 4, and 4 minus 5 is negative 1. Now remember that these 2 vectors, directions, have to be non-collinear. In other words, they can't be scalar multiples of each other. As you can see, 2 times the value 1.5 is going to be 3, but 0 times 1.5 is not negative 4. So these are not scalar multiples of each other. So now that I have that information, I can write the equation as a vector equation. So I can write as r is equal to, pick one of the points as a vector, 2, negative 3, 4, doesn't matter which one, plus some scalar multiple of one of the directions plus some scalar multiple of the other direction. And again, because there are different ways that you can choose different points and different ways you can choose directions, there could be multiple answers that you get here. And thus concludes this lesson.